Hello, dear professor and my classmates. I'm Songjin Nan from Gene Expression Research Lab. Today, I will present my own project, in vitro selection of DNA aptamers that bans insecticide. Firstly is my goal. My goal is to get the specific aptamer can bind my target. My target is insecticide, such as malathion or fipronil. And then, why should I do this one? As you know, fipronil and malathion, both of them are insecticide, so they can kill the insects. However, they do harm to the people's health. And the traditional detection method of fipronil malathion, like GC, LC, is low sensitivity and poor stability, and they are costly and easy to produce false positive. In this case, the aptamers can bind the fipronil and the malathion, so that is to say, the aptamers can detect the fipronil and the malathion. That's the reason I did aptamers. I will introduce my presentation in these two parts: introduction, methods, and skills. Firstly is the first introduction of malathion. So, what is malathion? As you can see here, malathion is an insecticide. It also can be used for public health, mosquito control, and fruit fly. It's also an ingredient for some special shampoo for treating lice. However, it is a toxic chemical, can increase the risk of liver cancer. It also can pollute the environment because it can mix with water and can move quickly through soil. It's fipronil. Fipronil is also an insecticide, and it also has some advantages. However, this one is also a toxic chemical, also can pollute the environment. So, the detection of these two chemicals shows very important. Then is aptamer. So what is aptamer? As you can see here, aptamer is just a piece of DNA, RNA sequence, or xRNA or peptide, and then by incubation it will have a structure formation. In this style, it has different secondary and tertiary structures. Then, when the target was added, it will bind to the targets with high specificity and affinity. So, the aptamers can detect the target. Why aptamers attract our attention? Here, I compared the antibody to aptamers. You can see the aptamers has many advantages, such as high stability, cheap synthesis, and easy modification, low immunogenicity, more varieties of targets. After this, what's more, the aptamers have many application fields, such as in the new drug delivery, diagnosis of disease, bioimaging, hazard detection, food inspection. In my case, my focus is in the last two areas, is the hazard detection and the food inspection. The second part is the method and the skill I used in my experiments. How can we get the aptamers? We can complete it by selects. In this figure, it introduced three parts of selects: library generation, binding separation, and the amplification. We can repeat it by 10 to 15 times, and finally we can get the aptamers. And I'd like to introduce every step in detail. It's the library generation. So, as you can see, here is an example of select library. So, this library includes 3 parts: forward primer, reverse primer, and between them is a random region. What's more, it has a 3 built-in in its 3 ends. This one is for the future fluorescence signal testing, and in Figure B is the inclusion style. And then in the Figure C, when the target was added, it will bend to the target in Figure C. So the sequence of this target is the aptamer sequence of our interest. So our goal is to get this sequence and predict its structure. The second part is binding and separation. As you can see in this step, a special base was used, and the library after the library incubation, we added it and let it going down. We washing with the select buffer, and illusion is our target. So in this step is to remove the unbound sequences. In here, a small scale PCR can be performed to check the results with the washing and illusion as the template. Second part is the amplification. After we get our illusion is our target, a large-scale PCR can be performed in here. We can get the library and get the DNA for next round selection or for cloning. The above part I have talked about the selection. And after we get the aptamer, how can we know this aptamer is we want? So we need to check it by validation. It's also the second method I use is the dissociation method constant measurement. In here, we need to measure the KD value. You can see the KDF1 in this figure. In the left of this inclusion, here shows the high fluorescence signal, and then we added the quencher. A quencher is a captured DNA. We can get the complex. So here is the KDF1. Then this equation is the KDF2. It starts from a complex of aptamer and the quencher. Then we added our target, and the fluorescence signal will increase. So here is the KDF2. So finally, KD value can be calculated by these 3 equations: KDF1, KDF2, and the KD value. So for easier to get the main point of KD value, here I give an example to explain. We can see with the capture concentration increased, the fluorescence signal will drop down. Here shows the KDF1. Then the target concentration increased, the fluorescence signal also increased. Here shows the KDF2. As you can see, the KD value, the final KD value can be calculated by the KDF1 divide KDF2. So here shows this KD value is about 6.1 micromolar. The third method I used is a TG method. In this figure is a quencher structures, but the quencher synthesis is expensive and hard to detect the fluorescence, and it is difficult to get the KD value. So Following this reference paper, we introduced a TG. TG is a displacement of pointer. So, how TG works? We can say here, a TG can make a complex with aptamers. Here shows the high fluorescence signal. Then, when it meets its target, it will shows the low fluorescence signal. So we can compare the high fluorescence signal to low fluorescence signal and get the final KD value. So that is the TG method I used. To get the TG method main point easier, so I give an example. Is my own result, my real result. You can see on the left figure, with the TG concentration increased, the KD, the fluorescence signal will also increase and will stable. Then on the right figure is my target. The target concentration increased, the fluorescence signal will drop down. And here is the KD EF2. So we can get the final KD value by calculate KD EF1 divide KD EF2. So here, this sensor is a good aptamer that can specifically bind to fipronil with good affinity because its KD value is a good value. We can check it. So here is the TG method I showed. Thank you for your attention. That's all my presentation.